Alright, so now today we're going to do two things. One is graph of functions, domains, codomains, and range. So I think in the last class we did expressing relations, and then how three different ways of writing relations, as well as what discrete and continuous functions are. So today we are going to look at these two things. Um, and of course, the first part here is you can recap from Form 2. The second part will be a bit new. But so in Form 2, what you probably did is that you have this kind of you might have this kind of chart, okay, and then you have x y table, yeah, not chart, sorry, 1 and 2, and then they will tell you, okay, y equals to 2x, so you fill up the table and then you plot the graph, okay. So you will then do, oh, this is -2, this is 0, this is 2, this is 4, and then what you'll do is I'm going to save a bit of time, but you will notice this if you actually do this example. um, okay, I'm not going to draw to scale, so I'm not going to follow exactly how many boxes and all that stuff, maybe, okay. As long as the idea is preserved. So you might have and then this might be your 4 points, okay. You'll realize that these are your 4 points. Maybe I should make this point go inside a bit. Doesn't quite matter, we are not writing it. So and then this is, so this is 1, this is 2, this is -1, okay. So you'll have these 4 points, and if you look at it, these points will all lie on a line. It lie on a straight line, actually. It's no coincidence, to be honest. Oops. Okay, I'll just try to draw some sort of line. So maybe this point is a bit out, okay. It doesn't quite matter as long as you get the idea, okay. So this is a line, and then you see all these 4 points will be on the line, okay, and this will be 2, this will be 4, and this will be maybe -2. Cool. Okay, so this is your y, this is your x, and then this is what you do. But pretty much you're already doing functions, you just probably were not told that you were doing functions, okay. So the only difference is that you're calling the output y and you're not calling it fx. So this is the same as saying fx equals to 2x, and what you're doing is you're just plotting some values, you're putting some inputs, okay. You're putting all these inputs into the function fx equals to 2x, and then you're getting these as the outputs, right? And what you how you're plotting it is just that your outputs are on the vertical axis, like we said the other day, okay. When we did expressing relations, right, we said if you do a graph, normally the output is on the the vertical axis. So this output is on the y-axis, not the x-axis, sorry. So it's the y-axis, and so that's it. This is the and that's what you're plotting, okay. You are so you're exactly doing functions, you just probably don't realize that you're doing functions, okay. So I'm just going to tell you something very generic. So now Oh yeah, another thing. So remember we did discrete and continuous last time. So when do we get a line and when do we get the points? I mean just four dots, because here we only have four inputs, right? So here I drew a line. So I mean I only drew a line because I'm assuming that, I mean I'm just under the assumption that, oh, okay, this is a continuous function. Well, if it's not a continuous function, then you only get the four dots. Okay, you don't have the line, but you have the line when, say, like I'm assuming that at this point here there is some output, at this point here there is some output, like all these are inputs. Okay, so like throughout this area they are all inputs, right? And that makes the function continuous. So I get a line. So cool. So what we saw just now is an example of a linear function. Okay, a linear function has the form fx mx plus c. Okay, m, c, these are all just constants. Okay, we call m the gradient, which is how steep the graph is, and c is just a constant. Okay, or the intercept. Okay, so c will be where the function cuts the y-axis. So now you have the graph. Okay, so earlier we did so in our earlier example we did fx equals to 2x, so m equals to 2, y, I mean sorry, so c equals to 0, right? Pretty much this is also equal to 2x plus 0, 2x plus 0. So it's as if we are saying c is 0. And what is the graph that we get? We get something like this, a straight line. Okay, we get a straight line. So linear means it's okay, so linear means you get a straight line. Okay, you get a straight line, and c is the intercept, and I said that this is this is not nice. So a straight line, and c is pretty much okay, it's a straight line. And okay, this, excuse me for my bad writing, this intercept is where it cuts the the y-axis. So in our example here, since c is 0, it is just cutting the y-axis at 0. Okay, and then m gives us the steepness of the slope. So here m is positive, right? So m is positive. So whenever m is positive, you, for a linear function, you'll get an ascending graph. Okay, so as x goes up, okay, as x goes here, your graph goes like this, right? So your y values are also going up, or your outputs are also going higher and higher. Okay, so that is linear functions. At the same time, if x is less than, if m is less than 0, okay, if m is less than 0, then you might get a line like this. Okay, in this case, can you tell me where the c is? So I just drew a random line here. Tell me where the c is. So c is where the where the line cuts the y-axis, the vertical axis. Okay, and in this case, why do we get a descending line? We get a descending line when this is when m is negative. meaning m is less than 0. Okay, yeah, we get it when m is negative. So the idea here is that if m is negative, just think about it. If this is negative, if x goes up, then you're multiplying x by a negative number, so then fx should go down. Okay, so fx equals to negative 5x plus 3. The thing is, if x goes up, say x goes from 1 to 2, okay, this term here, don't worry about this term, this is just a constant term. Okay, this term here goes from what, x goes from 1 to 2, so it goes from negative 5, and if you put 2 inside, it will go to negative 10. So negative 10 is smaller than negative 5, right? Because you're multiplying by a negative number. So that is the idea behind why you get a downward slope. Alright, cool. Then there are other functions. There is one that we call quadratic functions. Okay, quadratic functions will either be a u or an n, so it might be a u shape or an n shape. Important thing is that they always have this thing, maybe not here. Okay, maybe, I hope I'm drawing it at the right place, but we can't be perfect. Okay, so these two lines I've drawn here. Why have I drawn these lines? So in this case, in the minimum, and this case the maximum, so this is the u case. There's one u case and there's one n case. Quadratic graphs can be either one of these. Okay, it will either be a u shape or n shape. And this line that I draw, every quadratic graph has this line, and this is what we call the axis of symmetry. Okay, if you try any quadratic graph, okay, you will notice that it will be symmetric upon this, about this axis, meaning the left side and the right side will look exactly the same. It's like a mirror image, it's like a reflection. Okay, and what are quadratic functions? Quadratic functions are functions that look like this. So it's pretty much a linear function. Okay, it's like mx plus c, just b or m, it doesn't matter. Okay, so bx plus c, this is a linear part, but the difference is now that you have this x squared term here. Okay, and that is what will make sure that the curve is, the line is a curve and not a straight line. Okay, and when do you get the u and when do you get the n? You might be wondering, right? So you will get the u when a is greater than 0. You'll get the n when a is less than 0. There are reasons for this you learn in a future chapter, so I'm not going to touch too much on this. Alright, the third case, you don't have to really worry about this, is cubic functions. Okay, cubic functions, pretty much cubic functions can look like this, it can look like this, it can look like this, it can look like this. Oh no, not like that, sorry. Yeah, can look like that. So there are a lot of cubic functions, and that's because of the, I mean, cubic functions is a bit more complex than quadratics. It includes an x cubed term, so everything else is the same as a quadratic. Okay, this whole part is same as a quadratic, it's just that now you add another cube term to it, an x cubed term, so then you can get all these weird kind of shapes. Okay, I think I'll just touch on the most common part. So let's assume that these two parts are 0. Okay, if we assume that this is 0, then we can narrow down the shape to two kinds. Okay, it will either be like this, sorry, it will either be like this or it will be like the other way around. Okay, it'll be one of these two, and pretty much the d term here is like the linear case, okay, it will tell you where it cuts the axis. So okay, this is if you have a positive d, so you might have this one, maybe fx equals to 3x cube plus 5. Okay, if that's the case, then this is 5. Okay, this is the d. If d is 0, if d is 0, then you get something like this. Okay, my drawing might not be perfect, but the idea is that if d is 0, then it cuts the axis at 0, and if d is negative, it will cut below. Okay, it might be something like this. Okay, yeah, so that is that. And then it's not only this shape. Okay, I told you that it can be the opposite shape. And when does that happen? Well, that is dependent on a. So you get this shape, the one that I've drawn on the diagram, when a is greater than 0. Alright, but if a is smaller than 0, if a is negative, then you get the opposite kind of shape. Okay, you can get like this. So, okay, so this might be, maybe, who knows, fx equals negative 2x cubed minus 5. Okay, so then this will be negative 5, right? You must take care of your d. This might have some positive d here. Okay, but still a negative a. So this is a less than 0, a less than 0, a less than 0, and then this pink curves is a greater than 0, a greater than 0, a greater than 0. Okay, cool. Now let's talk about domains. So now we have done all these functions and all this stuff. Let's talk about domains. So domain is just defined as the set of all objects. So a set of all things that you're going to put in the function. Okay, it's actually the set of all objects that we consider. So normally you can choose the domain. You can choose what input I want to take. Okay, so speaking about that, oh sorry, a function is pretty much defined by two things. Of course, the first is the process. Okay, what are you doing to the number? Are you multiplying it by 2? So it's like fx equals 2x, or fx equals to x squared, or so on. Okay, defining what the function is doing. So that's the process. Second question you need to answer is, so this is what is the process. Second question you need to answer is, what inputs are we putting in? Okay, we can normally we get to decide this. Okay, so I'm not going to go too much into the intuition. If you want a separate explanation, I can provide it in a different video. Let me give you an example though. So I'll show you two functions that have the same process. Okay, it's both fx equals to 2x, it's just multiplying it by 2. It's a linear function, but in the first case the domain is anything that is between 0 and 2. So we are taking all the objects that are the objects x that are between 0 and 2. In the second case, we are taking all the objects that are between 3 and 6. It's a different domain. So in the first case, you will have 0, okay, and then all the objects between, maybe this is 2, this is 4, right, this is 0, and then you draw a line in the middle. So this is our first case. Okay, our inputs are only from here to here. Okay, this is our domain. So this entire thing is our domain. all the that whole interval is the domain. Next, let's look at the other function. So with a different domain, let me just extend this line further. So let's say this is 3 and this is 6. Okay, so it should follow the same line. So let me start somewhere here. Yep, correct. But this dotted line should not exist. Okay, so this will be 3. This will be the point for the input 3, and then you bring a line from there. Okay, and this will be the part for 6. So then you can see that this point links directly to 6. Okay, so this point this links directly to 3. And so if this is function 1 and this is function 2, then this is function 1 and this is function 2. It's not the same function, right? You see, because you have different inputs. For function 2, these are the inputs. This is the domain. Okay? So then let's talk about the range. Sorry, this video is getting a bit long because we discussed two things. Okay, we discussed all the graphs and then we're doing domains and range as well. The next two videos will be quite short, so just bear with me. The range is basically the set of all images. Okay, basically outputs, all images for the possible objects in the domain. So we have a domain, right? We have a domain. So these are the possible objects, and then you'll map them somewhere. Okay, so this is the domain. Say our domain only has 3 points. You map them here to these 3 points. So then these 3 points here is the range. Okay, it's exactly there. So this is a very important word here. It's exactly the set of all images for the possible objects in the domain. So nothing more, nothing less. Okay, cool. Then the codomain. Codomain is not a fixed set. The codomain is any set that contains all the possible images. Okay, and now hold up, we saw this with the range as well, right? Pretty much we said that the range is the set of all images, and then we say that the codomain must have all the possible images. So isn't it the same thing? There is one difference. You see how we say this is any set? So this means but the codomain can contain extra elements. So things that are not outputs, things that are not images. Okay, it can contain. So the idea is this is the range. Okay, so the range must be inside codomain. So this is the concept. Okay, the range must be inside the codomain. All the possible images must be in the codomain. Cool. Let's do a simple example, then we can get done with this class. So a simple example with 3 inputs. So this becomes automatically your domain. We are just taking 3 inputs and this is our domain. Cool. Now we have two more things. So -1 goes to 5, 0 goes to 10, 1 goes to 25, whatever. Okay. And then, so my question, what is the range? Well, the range is then just the set of all outputs, right? This is the range. We have 3 inputs, then we have 3 out. We happen to have 3 outputs here, so that's the range. Okay. If we only have 2 outputs, like say it's a many to one relation, then we only have 2 objects in the range. Okay. So the range is just all outputs. Okay. Now, okay, we say that this is the range, but can this be the codomain? Of course it can, because it has the range, right? It has all the outputs, right? So this, the range can be the codomain. No issue in that. Okay, it has all the outputs, it has all of this. But can we get a different codomain? Of course we can. Let's add 50 here. It doesn't matter. We already have 5, 10, 25. This is the only thing that matters. As long as we have 5, 10, 25, we can add 50, we can add 300, it doesn't matter. Okay, any set like this will be the codomain, as long as it has the range. Oops. As long as it has the range. The range must be inside the codomain. Okay, so I think we can be done with the class, and I'll see you in the next one, in which we will talk about composite functions, and then we'll finish up with inverse functions in another video. Okay, see you.